Red.
Lesson 33, factors of polynomial functions. We're graphing polynomial functions. Again, we started this back in lesson 28. So if you're not sure about some of the basics on this, you can refer to lesson 28. The main ideas that we're building off of in this lesson are the highest degree term, the term with the largest exponent, if you were to multiply it out, so in general form. That is the dominant term, and that determines what the behavior is at the extremes. For example, if we have y equals x squared, what happens for very large positive numbers of x? Actually, write this down. For y equals x squared, what happens way out to the right? Does the graph of this function go way high positive, very tiny positive, very tiny negative, or very large negative?
Very large positive.
Very large positive numbers. So the graph at this extreme goes up that way. For very large negative numbers for x, does it go large positive, tiny negative, or large negative?
Large negative.
Large negative. And we know what this basic shape looks like. It's a parabola. Right? What does y equals x? For y equals x cubed, what happens for very large positive values of x? Does y very large positive, tiny negative, or large negative?
Large positive.
Large positive.
Large positive. What happens for very large negative values for x? Large positive, tiny negative, or large negative?
Large negative.
Large negative. We know what this looks like. It looks like that.
So wouldn't that one be large positive at the top?
This one?
Yeah.
Yeah.
You said large negative.
For large negative numbers of x, you get a large positive number for y. Sorry if I didn't say it that way. That's what I meant. Okay, so now that I drew those nice and big, let's do that again with a few more. Make them tiny. Y equals x squared. What's that going to? That's going to look like this, right? It's going to look like this. Y equals x cubed is going to look like that. What's y to the equals x to the fourth going to look like?
An n.
It's got to go.
Oh, third doesn't it?
Way at this extreme, it's got to go up. Way at the left extreme, it's also going to go up because it's an even
Oh,
power.
is it like a W?
So, depending on what else happens in this function, it's either going to look like that, or it might have a little curvy part in the middle. But in any case, at the extreme right, it goes way up. At the extreme left, it also goes way up. Y equals x to the fifth. What's going to happen there? Large positive numbers for x.
They go up.
Large negative numbers for x.
Yeah.
Down.
Down. So we would have this basic shape. You know, it might do some loopy things in between. But in any case, at the extremes, at the extreme ends, this is going to go up, and this end is going to go down. So you notice it alternates between your your even and your odd powers. So any function that has a dominant term with an even exponent, the extremes are going to look like this. If it's an odd exponent, it looks like this. Even, odd, etc. All right, now so there's some other things that we're going to cover here. When we're graphing a polynomial, we want to factor it as much as possible first. Most of the time in a course like this, the polynomial will be given to you in its most factored form already, which is nice for you. There are some times that you will get some irreducible quadratic factors.
Blue.
So let's take a look at example 33.1. We've got f of x equals x plus 4. That's a linear factor, meaning if I graphed just this, it would be a line, times x plus 2 to the fourth power, that's 4, times x squared plus 3 times x minus 5 cubed oops, times x minus 7 squared. So in this example, we've got 4 linear factors, meaning that if we graphed what's inside each of these parentheses, that would make a line. This one is to the first power, this one's to the second power, third power, fourth power, but in any case, these are linear factors. This one here is an irreducible quadratic. What value of x would it take to make this equal 0?
Is there not any?
Not any real number. Is there any way that x squared plus 3 is going to equal 0?
No, actually.
Well, you could do that and then square root both sides, and you'd have plus or minus the square root of -3, which is an imaginary number, and we're not dealing with that. We're trying to deal with 2 dimensions, real x's and real y's. So, in graphing polynomials, if we have an irreducible quadratic, it is never going to equal 0, because we're only talking about real numbers. That means that remember when we graph things, or setting up our graphs of polynomials, or polynomial rational functions, we always put in there, where are the zeros and where are the asymptotes, right? This irreducible quadratic will not give us a 0 or an asymptote, because this factor can never equal 0. Now, all right. So we've got, where are our zeros? Do we have any asymptotes, by the way?
No. Because
That's
it's
right.
not a thing.
Because there's no division. We're not dividing by anything. So there's no asymptotes. And let's see, we've got 7 and -4.
So when we still flip the sign for where it touches and or crosses?
Well, I'll show you yes, for the odd powered ones, and that's what that's the irreducible quadratics, and your question, which is addressed right here, is what this lesson is all about. So 1, 2, 3, 4, 5, 6, 7, 8, -1, -2, -3, -4, -5. Okay. What does this factor tell us? There's a what? Wait.
-4. -4.
-4. What about -4?
There, it crosses somewhere.
Let's say there's a 0 there.
Oh, okay.
All right.
Yes.
There's a 0. I know what you meant, but we have to be exact now. We're more specific now. What does this factor tell us?
There's a 0 negative.
There's a 0 at -2.
And
What does this factor tell us?
There's a 0 at.
Positive.
There's nothing there.
This doesn't tell us
there's nothing
anything. All right. What does this one tell us?
5.
There's a 0 at 5.
there. And then there's a 0 at 7.
And this one tells us that there's a 0 at 7. Sorry for my wonky x-axis here. All right. So there's our 0. There are our zeros. We have no asymptotes. If we were to multiply, what would be our dominant term if we multiply this out? X to the what?
Third.
Fourth.
-1.
Well, this is going to give us an x. This is going to give us an x to the 4th. So now we've got x to the 5th, x to the 7th, 8, 9, 10, 11, 12. If you multiply the whole thing out,
So add multiply.
right, the highest powered term is going to be x to the 1 plus 5 plus 2 plus 3 plus 2.
What?
What did I do?
I'm confused.
Because you're.
If I were to multiply this all out,
Yes.
distribute everything,
And then group them
into
together.
one big long,
Wouldn't it be
2 to 12.
Yeah, it would have to be 12.
yes, the highest powered term would be
10, 12?
x to the 12th.
Okay.
And is that going to be a positive x to the 12th or a negative x to the 12th?
Positive.
Wait.
How do you know that?
Yes.
Well, we're going to have a positive x to the first power times a positive x to the 4th power times a positive x squared times a positive x to the 3rd power times a positive x squared.
So yes.
Yes.
So it's good. So our dominant term is going to be x to the 12, whatever the coefficient is, and it's going to be positive in any case. So that means, so we have so our dominant term has an even exponent, and it's positive. What's going to happen for very large x values?
Up.
Up this way. What's going to happen for very large negative x values? Up. Also up. So we have a positive, even-powered dominant term. So at the extremes, we're doing this. So at the extreme, it's going up. At the extreme, it's going up. So in the middle, we've got zeros at these places. And let's see. So here's the other new concept from today's lesson. Linear factors that are raised to an odd power. This is what we've been doing. That's where it crosses the x-axis. So that is going to be. So this one. So it's going to cross the x-axis at this one, and it's going to cross the x-axis here. So cross at 5, and it's going to cross at -4. So if we've at the extreme, it's going up, and this is the first zero we get to, and it crosses there. We have to cross.
Oh, it's just gonna bounce off the negative.
And it crosses at 5, but don't know that yet. And at any linear factor that is raised to an even power is going to touch the x-axis but not cross it, bounce as you said. So that means we're going to have a bounce at -2 and a bounce at 7. So at 7, instead of, when it comes down here, instead of crossing it, it's going to actually go back. But then the 0 at 5 is going to cross. So it's somewhere it's got to come back, it's got to cross here. And at -2, it's going to bounce. And then it's going to cross at -4.
I understand.
Wow.
This is so new.
Bounce is actually a very good word.
Did we learn some of this last year? Because I feel like we did.
Yeah, I think
Very,
we probably.
very.
Yeah, at the very end of the Saxon pre-calc book, it does have.
Like vaguely touched upon.
Yeah.
Yeah.
It makes a lot of sense.
Like maybe we did it like 2 times.
Yeah.
I was thinking about how I'm going to take calculus in college, and I was like, oh god, what am I going to do?
The camera doesn't want to hear about your struggle.
Okay. So this is an example of how you break down what each of these factors does for the graph. Okay. So if you haven't already, at some point, this is what you need in your notes to help you out. Now there's one other. Actually, let's do one more example.
Great.
Whoa. Before we hit the other part of the lesson, which is very short. This
More.
example here, yeah, not much. Example 33.2 is multiple choice, basically. 33.2. We have a function y equals x minus 1 squared times x plus 2 squared. And it gives 4 graphs there, and we just have to choose which one most resembles the graph of this function. Well, based on what we know here, we're going to have, what are the zeros of this graph?
1 and -2.
So the zeros are at x equals 1 and x equals -2.
And they're both even.
And is the 0 at 1, is that a bounce or a cross?
Bounce.
Okay. What about the one at -2?
Bounce.
Okay. So both of these are bounces. I don't know if other math teachers or math books use that phrase, but I kind of like it.
Well,
It's very
makes
descriptive.
sense.
And then the other question is, what's the dominant term in this?
4.
It would be x to the 4th,
Oh,
positive
right.
or negative?
Positive.
Positive. So we know that at both extremes, it's going to go up.
So it's like a different.
So it could look like, actually usually,
Would it just be,
it
negative?
usually kind of flattens out like this, or it might have some stuff like this in the middle. We've got two places where it bounces. So in all likelihood, the graph looks wherever the y-axis is. Oh, let's see. This is probably the bounce at 1. This should be the bounce at -2, and so there's something like that. So then it's just a matter of, which of these graphs.
And because they're even exponents, we know that they bounce.
Yes.
Yes.
Okay.
So like if it was a negative x squared, is that when it, because you're like, oh, x to the 4th.
It would-
Flip
suppose there was a negative
Yeah, what are they on
out here,
negative?
then that would just flip the whole thing.
Okay, what is just out of the parentheses?
What's that?
When it's just outside of parentheses.
Yep. Or if there was a, say this one, maybe this one might say negative x squared plus 3 or something like that. So just pay attention to the highest powered x terms and keep track of it as you figure out what the dominant term would be. I've actually covered most of what was coming on page 179. There's a couple of comments on 178, 179. Was there another color? Blue. Page 178, with graphs of polynomial functions, there's this idea of turning points. Right? For a parabola, y equals x squared, right? We know that it goes up here at this end and up at this end. How many turning points does that have? Does a basic parabola have? One. There's one turning point. Right? It's coming along down negative, and then it turns and goes back up positive. So a parabola, y equals x squared, it turns and goes back up the other direction.
So it's one turn.
So it's one turning point. Y equals x cubed, right? Looks like this. So it's coming down, and a very basic one, like levels out and then turns. For it happens to be one turning point. Now, if there were other terms here, if it was y equals x cubed plus 2x squared minus 5x, or if there was other terms here, blah blah blah, then instead of just leveling off here, it might do this. So it might be have a turning point and then another turning point before it goes back up. So depending on what exactly it is, there might be only one turning point, but there could be two. Can't be any more than that. And so what the turning point theorem says, whatever your highest powered term, your dominant term, whatever that exponent is, if you subtract 1 from that, and that is the most number of turning points that the graph could have.
So it's like x to the 5th, and it'd be 4 turning points?
Yeah. So if we have an x to the 5th function with who knows what after that, we know it's an odd power, so we know that at the right extreme it goes up, at the left extreme it goes down, and depending on how it is, it might look like this. It might only have the one turning point. However, depending on what these other terms are, it might do something like this. It might have 1, 2. But it might do this. It might have 1, 2, 3, 4 turning points, depending on what the terms are. But it can't have more than 4 turning points. And that is enough to do the lesson.